feet. Many of us have them, but not all of us understand the differences in sizes. I'm the Great Orbax. We're here today with Dr. Mike Massa to discuss the concept of scaling with something that many of you have on your feet often. Dr. Massa, we have one of his sandals here, and of course, I can take off. I have one of my sandals here.
Don't say it.
Now,
Now, when we compare two sandals, they're the same shape, but different sizes, what we say is, since their shape is the same, we call that isometric.
now this one is much bigger than this one.
Right.
And in reality, it's 4 times the size. Now, what does that mean? When I say that, what I'm saying is that it's 4 times the length, 4 times the width, 4 times the thickness. But it doesn't necessarily mean it's 4 times the mass or 4 times the volume. We can come up with those relationships, and actually determining those is what scaling is.
Exactly, yeah.
So let's do a comparison. My shoe is 4 times the length of your shoe.
All right, so the length of Orbax's is 4 times the length of mine. Sometimes when we do these comparisons, we won't deal with the numbers, but we still want to make a comparison statement. So it's often convenient to talk about things in ratios. So let me bring this to the bottom here. Let me write, it's the same information.
But now we're just left with one number. So the ratio between the length of my shoe to the length of his shoe is 4. So let's now discuss the concept of, volume, right? We've got volume is length times width times the thickness of this material. So that volume will go as a length, and a length.
Right.
So L cubed.
Right, and regardless of the particular shape, it's always, a volume's always a length times a length times a length. So let's use this as some representative length. We're going to say that V is proportional to L cubed, or coming back to ratios, if we compare the volume of your sandal to the volume of mine, that's going to equal the ratio of lengths cubed.
Okay. Giving you 4 cubed or 64.
Okay.
Now that's an interesting ratio in terms of the volume, but what does it tell you about what anybody would care about? We're not filling this with water or gummy bears or Smarties. But we might need to talk about how much material costs per volume.
Right.
Or you might even want to talk about the actual mass of the sandal itself. Mass goes as the volume, right?
Right. As long as we're talking about two things that have the same density, right? Density times volume gives us mass, then that's the same comparison.
Now, one of the things to ask yourself is, when is this going to change? This probably makes sense to you, except for where maybe I got this giant sandal from. But when does this change? Well, let's specifically look at the outline there, or what I can say in terms of the shape of this sandal. This maps out a certain area, and it literally is a footprint, right? It's the footprint of this sandal. Dr. Massa's area over there is much smaller, but how much smaller is that area than this one? How much bigger is my footprint than Dr. Massa's? This comes back again to this ratio and looking at how these work.
Right. Area is always a length times a height. In the case of a circle, it's r squared, pi r squared.
So it's always in length squared.
Right. So we'll say that the area is proportional to some length squared. And when we compare these two footprints, the area of Orbax's footprint to mine, that's going to be proportional, each term, L squared, so L naught over LM squared.
Right. A contribution from each of these.
Right. And so then the ratio of areas is just that factor 4 squared here, which is 16.
So my shoe is 4 times the linear dimensions. It is 64 times the volume or mass, and it is 16 times the surface area or the footprint.
Yeah, and that's basically how scaling arguments work.
Wow.